Hi, everyone. This is the Hungry Math Professor here, and thank you for coming to my channel. Today, I want to talk about the principle of explosion in logic, and we're going to do this slightly informally because I don't want to study mathematical logic. Formally, you should talk about how to introduce logic itself, and then you should do some model theory, some proof theory, talk about the rules of logic, the assumptions, and things like that. But I don't want to get into all those details. So instead, I'm just going to assume we have some axiomatic system in standard logic. If you've ever studied logic in a math class and you were introduced to some elements of standard logic, perhaps in an informal way, but that's okay. And if you want an example for an axiomatic system, you can think of ZFC set theory, which we usually think of as the uh, foundation of mathematics. And there are other versions of set theory that can also play the role of foundation of mathematics. And if you like other examples, you can just take the axioms of a group as an example of an axiomatic system, or Peano's axioms for number theory, the axioms of a ring, and so on and so forth. Um, but any axiomatic system is going to be fine for this discussion. And we need to make an assumption. We're going to assume there is a statement P. So this statement is something that can be made in the axiomatic system, we're assuming in standard logic, which can be proven to be both true and false. Now, normally we think of this as a contradiction and we don't want such things. But now we want to see, what if such a thing is in our system, what happens? Like, why are we trying to avoid these things? Besides the obvious thing that we don't like things to be true and false. Um, why are we trying to avoid this? So another way of saying this, by the way, is that we're assuming that P and not P are true, so that we can prove them to be true. And so another way of saying that is we're assuming that P and not P is true. Okay, I'm really just restating the same things here in different ways. So I'm not making three assumptions. I'm just restating so you get the idea of what's going on here. Normally, we don't like these things, and we usually think of P and not P as being a contradiction, something that could never be true. But we're assuming that we're in a system that has a contradiction. We want to see what happens. So now let Q be any other statement in the axiomatic system. Okay, we don't know anything about Q. We're assuming we don't know anything about Q. Okay, again, I'm going to do this a little bit informally, but let's see what happens. So now notice that P and Q is true. No, I want it the other way around. Sorry. So P or Q um, is true since P is true. If you remember ORs, you only need one of them to be true for the OR to be true. Okay, so P or Q is true. Now, let's just remind ourselves that not P is true, or I want to say it differently, sorry. P is false since not P is true. Depending on which of the assumptions I restating, you might not have to say this, but I want to remind you. And then now, since P or Q is true and P is false, we see that Q is true. We don't know anything about Q, but we can show that it's true because P is both true and false. Now, since Q is arbitrary, we can repeat this argument with not Q. So sorry, since Q is arbitrary, we can repeat this argument with not Q. So from just assuming we have a statement P, which is both true and false, we're able to show that Q is both true and false. Again, Q is arbitrary, so we can show that any statement in our axiomatic system is both true and false. That's the conclusion that we're coming to here at the end. So any statement in this axiomatic system is both true and false. And that's the principle of explosion. Basically, you just need one, once you have one contradiction, P and not P, then you get that every single thing can be proven true or false. So it just immediately explodes from one contradiction to everything being a contradiction. And what are we to make of this? What are we to make of the principle of explosion? Now, in the standard logic, and most mathematicians, I don't think I've ever exposed to this, and there's a good reason for that. I think, as mathematicians, we want to avoid contradictions. So we're not so bothered by this. Yeah, if a contradiction is in the system and it explodes, maybe that's a good thing, right? Because we don't want it to be there in the first place. So maybe the explosion is like a good signal that there's a problem, right? And we want to avoid contradictions. So we want to look at systems which do not have contradictions. And there's no real problem with the principle of explosion, I think, from a mathematician's point of view. And even from the standard logician's point of view, I don't think there really is a problem. And I'm not really, my goal not here to convince you that there is a problem per se, but I want to introduce some tension into the game and at least explain why you might want to consider a system of logic which does not have the principle of explosion baked into it. And so let me try to do that now. Well, first of all, remember that Gödel's incompleteness theorem, the second incompleteness theorem, means that we can never prove that a system is consistent. Or consistent means that there are no statements where they're both true and false, right? So basically, we're working, when we talk about the principle of explosion, discussion I just did, we're discussing an inconsistent system, right? And it would be desirable to know that a system that we care about, like ZFC set theory, is consistent, meaning there are no statements that can be proved true and false. But Gödel's second incompleteness theorem shows that that's not possible. You can never prove from inside the system that a statement is that no statement is both true and false. There's some philosophical questions here too that about like even if the system could prove that it was consistent, should we believe the system's statement about its consistency? Other approaches is we can build a bigger system which contains a smaller system. Inside the bigger system, we can show the smaller system is consistent, but should we buy the larger system's claims? There's lots of like philosophical questions about that, which I wanted to bring up, but it's not the focus here. Instead, the question is, maybe we should just embrace some inconsistency, right? Another way to think about it is this. When Frege produced his logic, it's famous that Bertrand Russell and also Zermelo, it turns out independently, noticed that there was a paradox called the Russell's paradox or Russell-Zermelo paradox, which is pretty famous. I did a video on it that you can check out if you're interested. And when we say a paradox, we also mean a contradiction. It's a statement that's both true and false. And so that's a problem, right? Because the principle of explosion means once Russell's paradox is in the system, the entire system explodes and everything becomes true and false. That means Frege's system was useless, and that started the look for other axioms to get rid of that. And we've solved that issue. We know how to remove Russell's Zermelo paradox now. But the point is that we don't know if at some point we're going to come across another contradiction like that. We can't prove that it can't happen. And so we have no reason to know one way or the other whether ZFC set theory is consistent. We just don't know. For all we know, we could creep up a contradiction in the next couple of years, in the next couple of days, who knows? And so what are we supposed to make of that? Does that mean that all the mathematics that people have done in set theory and all the mathematics that are built on top of set theory is wrong? I don't think that we would feel that way. I think we would feel that most of the mathematics we've done is actually correct. And so we might respond by saying, okay, let's just tweak the axioms a little bit, right? We probably just need to tweak the axioms and then this contradiction will go away. But the tension there is that in that case, if we found a contradiction in ZFC set theory, ZFC set theory has been around for a long time. So it's possible that that contradiction is so complicated to get rid of that you wouldn't just be able to make a small tweak in the axioms. You might have to make a huge tweak in the axioms. And if you make a big tweak, even a small tweak in the axioms can produce very different mathematical results built on top of that set theory. So that might not work, right? We might not be able to make a simple change to the axioms, which alleviates the contradiction. So what are we supposed to make of then, right? Is all the mathematics we did worthless because of the principle of explosion and this one contradiction we found? Or is it possible that everything we did in ZFC set theory is still correct and valuable, and this contradiction just needs to be taken head on and just accepted? Maybe we don't want to think of it as true, but maybe we just allow the system to contain these contradictions and we don't let the principle of explosion cause the entire thing to become worthless. I think from the point of view of Gödel's second incompleteness theorem, this is a completely reasonable idea. And, so this has been around, actually. People have been criticizing this kind of thing since Aristotle's logic, and certainly more recently, it's been around in the form of what's called paraconsistent logic, where people adjust the axioms of logic to allow for contradictions without the principle of explosion. And so I did this kind of informally, so you don't see the formal logical issues here. But basically, we took a or statement and we concluded that Q had to be true because P or Q was true. So you could try to weaken that and get rid of that, right? Get rid of that ability to make that conclusion. And there's other things you can modify. I don't want to get into those details yet, but this is an area of logic. There's a whole bunch of what we call non-standard logics where people challenge some of the claims of standard logic and adjust and see what happens, right? The famous one was intuitionist logic, which was introduced by Brouwer, and he introduced a whole intuitionist mathematics by Hayting on top of it, and this whole intuitionist project, which ultimately failed in the sense that the mathematical community did not adopt his system, but it didn't fail in the sense that it was a perfectly reasonable system that was put down that one could build mathematics on top of. And people still study it, even though it's not studied by the most of the mathematical community. So this is a question, what is the right logic to use for mathematics? And what is the right logic in general? Is there a right logic? Or should we just be pluralistic about logic and pluralistic about mathematics? I'm not going to answer these questions for you. I'm not sure that there are easy answers here, but I will do some more videos in the future on pluralism in mathematics, paraconsistent logic, and intuitionist logic, and various other things that you can look forward to. So let me know what you think. How do you react to this feeling of perhaps changing standard logic for some other logic? What do you think about that? Like, comment, and subscribe, and I hope to see you at another video.